To create this video, I partnered with DesignCon. In this video, we are going to learn how to simulate power supplies. We will use this board as an example, but basically everything what we are going to talk about can be applied on any kind of power supply. And we are going to learn not only how to simulate it, but also how to improve it, how to, fix it, how to make some changes. Is it correct, Ben?
Yeah, correct. Yeah, we're going to have fun here. We're going to show some cool things and have a great example from a paper that I did with some great colleagues, Steve Sandler, Heidi Barnes, and Christian Yachts at TI. So it's going to
Okay.
be a lot of
Okay, so first, I always wondered like how to simulate power supply because power supplies are usually a chip and then some passives around the chip, and all these chips they are a little bit different. So what is background of this simulation? If I understand right, we actually simulate what the power supply does. We don't have to simulate the physical chip, every single chip from different manufacturers, correct?
Yeah, so we have a model, a behavior model that
Mm-hmm.
we created in Keysight ADS that basically models this power supply and any parameters of that power supply, like slope compensation or gain parameters that you want to vary based on manufacturer tolerances. That's part of that behavior model.
Mm-hmm.
And the main reason why I use ADS to do this sort of modeling from a power supply perspective is it comes down to, from a power integrity perspective, I care about everything from the load to the power supply or VRM, right? Depending on what field you're in, you might say VRM, voltage regulator module.
But
And so that,
theoretically, any simulator can be used.
yes, but the problem is, right, like LT Spice is a great example. Even TI's tools are great. The problem is all of those, they have fidelity gaps. How do you include the port effects?
Mm-hmm.
How do you include those additional parasitics that actually affect your power supply performance? And this is a huge gap in the industry. And as we get more and more complex, higher currents, right? This example here, this TPS 7H4003, it's only an 18 amp power supply, right? But this was designed specifically by TI to support rad tolerant applications and targeted for the AMD Versal or Xilinx Versal, if you're still used to saying that, which is a really high current FPGA, right? I mean, the Versal can pull over 100 amps. So you can build a multi-phase version of this board. In fact, TI has done that, and so have a lot of people, where they will have like 4 to 6 phases of this VRM on the same board to meet the current requirements of the Versal. And so when you do that from a power integrity perspective, you care a lot about all those parasitics, right? You're talking about having good cap models, good models for your PCB. It doesn't stop at the point of load. And this is what I want to show folks today. And this is why we did this paper at DesignCon. And we even presented some of this at APEC this past year.
Mm-hmm. Okay, so let's be a little bit more specific. Let's have a look what we have on this board. And again,
Sure. Yeah.
I would like to point out this is not chip specific. It will apply on any
Yes.
power supply.
I build these models all the time. And I've built these models for ADI VRMs, TI, Renesas. It's not like a specific chip specific to your point, Robert. In this case, I have a great example here that made for a great teaching demo that is for an 18 amp, buck converter that is rad tolerant, but it doesn't matter that it's rad tolerant or not. This is just neat that it's rad tolerant, which means it's for space applications, right?
Mm-hmm.
Like LEO, GEO sort of applications, if folks are familiar with that. And it's an 18 amp buck, 3 to 7 volts in. And our demo here today, we're going to show 5 volts in, and we're going to be regulating it down to around 1 volt.
Mm-hmm.
And yeah, I mean, it's got an integrated switch, half bridge switch, and all you need to add is your external magnetics
Mm-hmm.
and your right, your power distribution network.
And what we will get with this simulation, we can tweak, for example, output capacitance or these,
Yes.
I don't know, other components for feedback or for something, or how this
100%.
simulation will help us.
You can see in real time, right, what your output ripple looks like. You can see your output impedance, your PSRR. You can look at your open loop gain if you want to do that. And then you can see how with your PDN, how all those components are affecting the overall performance of your power supplies from a noise perspective, from a ripple perspective, and then add in your load. If you wanted to go a step further with ADS, you can do that and model, okay, are you meeting your compliance specs for voltage, AC and DC voltage specs, which is really what matters at the end of the day, right? Steve Sander likes to say, in his old school days when he was initially designing power supplies, he likes to tell a story about he had a boss. He said, look, Steve, power supply designers have one job, and it's to make the load look sexy. And that's really what we're trying to do here today with the power supply. What matters is what the load wants, right, at the end of the day, and that's power integrity.
And simulation is easier because you don't have to physically build it, but you can just click, change it, and then you see the results immediately.
There are blocks, yes. You're just connecting these blocks together. You're setting your resistor values and adding in your cap models and your board effects. And yeah, it's not super complex.
How close the output from the simulation is to the real thing?
I will show you that you can get pretty much the exact same result.
Wow. Okay, so let's have a look. How can we build model of this power supply?
Sure. Yeah. So to build one of these state space average models, we call this the Sandler state space average model, since Steve Sander created this for ADS. This is what Steve Sandler teaches. He calls the unified state space average model. And so it does do DCM, it does do CCM, does voltage mode and current mode, all unified in one model.
Show the model. I'm curious. What they are talking about.
Sure. Yeah, sure. This is the model. Here it is. Yeah. This is the model I built in ADS, and this is a measurement-based model.
So this is the power supply. What we
Can
you explain a little bit more what we see here?
Sure. Yeah. Can you see it? Okay. Do I need to make it bigger?
Yes. You can make it full screen maybe because the letters are like super small. But yeah.
Okay. Sure. Okay. So, what's unique about this model is you get the small signal and large signal components.
What does it mean, small and large?
So for example, right, when we talk about like a small signal model, like a great example that I'll use Steve again. He likes to challenge people, and he'll say, okay, you showed that your power supply is stable with a Bode plot, but then you did a step load to check stability. But you already showed that it was stable with a Bode plot. Why did you do a step load if it was already stable? Did you need to do it? And it's a trick question. What he's trying to get you to realize is that the Bode is a small signal model, and the step load is a large signal model. So when we talk about your output impedance, that is a small signal model. And when we talk about like switching, ripple, and transients, that's a large signal model.
Okay.
Right. And so we get all those components here. So you want output ripple, you get that, right? You want your simulated voltage response. That's like, non-transients, that is a small signal model.
And you can simulate all these with the model.
Yeah, it's a unified model.
Wow.
Yeah. So PSR, all those things, right? Those are small signal models. So we get both large signal and small signal components in the same model. And that's what's powerful. But like any VRM, right? I mean, it's pretty standard, right? There's a buck block, and there's a bunch of equations in here that define this behavior model. We don't need to worry about any of those equations. What you need to understand is how to set the gain parameters for this model using data sheet or measurements that you would make. And we talk about that in our paper, right? So I've already done that here, right? So there are two gain parameters that characterize what we call the plant, which is this block here, and that's RI and VRAM, okay? And this is a great example to learn how to build this model on, because TI, the space group, in their data sheet, they put those gain parameters right there in the data sheet.
Can we have a look? Because I just would like to know where you get these numbers,
Yeah, sure. Yeah, no problem. So here in the slide, right? So this is right from the TI data sheet. I'll show you right here, right? So you see I'm calling comp to iSwitch GM, okay? So if I go down here, right in the data sheet, scrolling down, just bear with me, to iSwitch GM, almost there, right here. So right here, they're giving you RI, right? Comp to iSwitch GM. And so they're saying at 25C, which is what I'm looking at, 40 Siemens, right? 1 over that is 25 milliohms, approximately 25 milliohms. And so that is RI, okay? Now, they're also giving me the slope compensation, which you solve for ramp using an equation based on an external resistor in here, right? And that is, there's another equation in here that they give you. Oh, I'm just gonna flip back to the slide, but it's this equation right here. It's in the data sheet. And so this RSC is just a resistor that you set outside the part. Okay, and so you put in the value there. And so what you can do for that slope comp, right? You solve for slope comp, and I walk you through the math here, right? So here I solve for slope comp using that RI value that we just talked about. And from there, I need to figure out my slope comp per duty cycle, right? And so if I'm setting a 500 kilohertz switching frequency, my duty cycle is 2 microseconds, right? And so I'm just multiplying my period. I'm sorry, my period is 2 microseconds. So I'm multiplying my period by my slope comp, right? Which I showed you how to solve for using this equation. And then I get 2.2 amps per 100% duty cycle. Now to find V ramp, it's just V ramp times this slope comp times RI.
I'm telling you, I'm lost, but I believe someone who really understands power supplies, they definitely know all these parameters. If not, and if they would like to simulate power supplies, they would go search for exactly what these parameters are about and then find out these parameters for your specific power supply, correct?
Correct. And so what we're doing is we're basically just setting those two parameters, right? That RI and V ramp in this block and in this block here. And we're basically setting the open loop gain, right? When we say open loop, right? Open loop means we just want to see the gain of this plant, right? We don't want to include the feedback loop, the air amplifier. We don't want to include any of that. We don't care. There's a gain from this resistor divider, right? There's a transfer function here. There's also a gain that is multiplied by this gain from this air amplifier. We don't want to see that. So what we do is we inject a voltage here at V comp, which opens this loop. Okay. And that's what we're plotting here. This is that open loop gain, right? And so ultimately, this is how we characterize that. Now, once we have that, you can get these numbers from measurement if the data sheet doesn't give it to you. Okay. And we talk about that all in our paper, how to do this. You know, if you're working with a manufacturer, they're being stingy, right, with this information, you can measure it yourself. I do it all the time. It's not rocket science. Honestly, to build a great state space average model, it only takes 5 measurements. You need to measure your on and off output impedance. You measure RI, and you measure open loop and closed loop gain. So open loop is what we're showing you here, and I show you how to do the measurement in this paper. And then closed loop gain is what people could call PSR. So it includes your everything, your PDN, your feedback network, the air amplifier, everything.
So if I understand right, when you take these parameters, what you just explained, you fit them inside of this model, and that's basically how you create your specific chip.
Exactly. So what we did here, right? So kind of jumping ahead on the slide here, where we started using the datasheet parameters for nominal was this black line, okay? So I made some measurements, right? And then I just tuned the red line to match the blue line. Now, this matched line, this red and blue tuned line here represents the actual device that I measured, right? This one. It's still within the datasheet parameters, right? So you could just stop with this if you had datasheet parameters. But if you wanted to see an exact measurement correlation to ripple, you need to make sure your gains are exactly what you have set there, right? So, and that'll be important when we talk about the time domain ripple and you see how the ripple matches verbatim. That's because our gains are set correctly for the device that we use for correlation, right? So these are just little nuances that you need to be aware of, right?
Okay. And so where can we find the information how you can measure it? You mentioned a paper.
Yeah, that's in this paper too. So like we show you the measurement setup. We talk about it. There's stuff online.
So
I have stuff on
it is in this presentation how to measure it.
Yeah.
Oh, we are going to talk about it today.
I mean, you can if you want. There's a lot here. We can go in that detail. Robert, I'll let you lead me. Where would you like to go? This is a PSR measurement. It's a 3-port measurement. You have to have some sort of line injector that's modulating your power supply input. And you have a probe of your input of your power supply and a probe of your output of your power supply. And I'm using a VNA, in this case, a Bode 100, to make this measurement. Now, to do the open loop, all I'm doing is I'm injecting a voltage at the V-comp pin to open the loop, right? And to do that, I'm using the J2103 from Picotest. Now, you could just use another power supply. I like the J2103 because it's a floating battery-powered device that actually opens the loop, but it still regulates the power supply to keep it from going into an unstable point. And it does that because it still has a sense point at V out that you connect. It's very easy to set this up. That's why I like this device. So it makes it very simple. But you can see there's a lot of wires here, right? There's a lot of stuff going on. It's kind of scary looking, but it's not, right? This is not that scary to do, to be honest. And then we talked about the impedance, right? So let's talk about that. So we talk about impedance, right? So this is what we're talking about with impedance. So we're measuring across an unused cap pad, and I think I depict it right here. So right there, that is C23 is what I say there, right? C23, we just put a 2-port probe at V out across this unused cap pad. And again, I'm using a 2-port probe from Picotest. This is the only one that I know of in existence, and I'm a huge fan of this probe. It's very easy to use. I actually have a video on my channel that walks people how to do the full calibration. And you can get in a really good noise floor with this probe using the setup that I'm showing you here in this picture. So if people want to watch that, they can go to my channel and watch how to do the calibration. It's about 30 minutes. I'm going to make a shorter one here soon, but there's an app also out there that I wrote with Steve. People can also reference if they want to read that.
So what we measure impedance for every frequency or something, and then how do we?
Yeah, so we're measuring close to DC, and I think in what I showed in the plots is around 10 hertz is where I start, and we go out to 50 megahertz, which is the limit of the.
And how do we use these results? How we put these results into our model?
So the important thing about impedance, and this is something that I teach. Impedance is super important to your from power integrity and a PDN perspective when we talk about power integrity. And if people walk away with one thing, and they have one thing that sticks with them, it's that I want them to remember this. It's that noise follows impedance always, right? So what your impedance looks like, what it's doing, if you have any high Q points in there, those are potential points for oscillation. You can use NISM, non-invasive stability measurement, which was also invented by Steve Sandler. He won Engineer of the Year at DesignCon 2023 for a reason, right? He's done some amazing things. So that being said, you can use NISM, do an impedance measurement, use NISM post-process and check stability of your PDN. And what NISM does through using an impedance measurement is it's mathematically cutting the trace and looking at the source and the loads at the same time. And you can assess stability of your PDN without having to inject anything in the control loop, right? Because remember, our control loop adds inductance that affects our overall PDN impedance. And that's really powerful with the fact that we can use impedance to assess that. Because the challenge today is if we're looking at a PMIC, right, where you don't have access to the control loop, how do you use a Bode plot? You can't, right? And so because we're doing impedance, we can still do a Bode plot, right? We can extract the loop gain because the loop gain is just on over off -1, right? We do an off impedance measurement. We do an on impedance measurement. We can plot the extracted loop gain just like that. In fact, I show you in this paper, right, that I did with Steve and Heidi and Christian.
But how do you incorporate these results from this measurement? You don't. You compare these measurements with the simulation results, and then you try to adjust your simulation results to meet the measurements.
Yeah, I'm using tuning my model.
Okay, I understand now.
That's what we're doing, right? So we're tuning. That's what we did here, right? So this is where we started. Basically, I put the parameters in the model, and this is where I started, okay? And then after tuning the model to match this blue line, this measured blue line, I brought the red line over that blue line by tuning parameters in here.
So basically, everyone can start with datasheet only, but if they really would like to be accurate, then they should measure all the kind of things, and maybe that's for another video.
100% yes, and I'll just add one caveat. It's assuming the datasheet includes all these parameters.
Okay.
Not every vendor datasheet includes these, so that's where you need to be able to make them.
Okay, if they don't include it, then measure them. Okay,
Yep.
so let's go and let's have a look on this model. Can we talk a little bit about each individual part of the model?
Yeah, so okay, so here you can see there's really...
Start with something simple, load. Where is the load?
Oh, here I'm just using a DC resistor for the load, right? So I'm just applying a DC load using a resistor. I can do all sorts of load in ADS, but here I'm just using a resistor. I could do a pulse, I could do a step, I could do all sorts of things. But in this example here, we're just using a resistor.
And where do you set up what the load is changing, or?
No, it's static.
Here, there are variables. Okay, I see.
And so here you can see it's just a 0.1 ohm resistor, right? That's what's set there.
Okay. Then on the right there is, what is there? Termination, or what is it? 50 ohm?
Here. Okay, so this is right here. These things. Yeah. So there are some measurements that I did, right? So I had to measure my on and off impedance measurement, and I brought those in these blocks. So these are the actual data that I measured and exported.
So you can compare them?
Yeah,
okay,
exactly.
Okay.
So I had to bring them into the simulation. That's what these three blocks are, right? So this one is your PSRR. This one is my output impedance both on and off, right? And so this is what I'm showing you in these two boxes here. Okay, and the impedance, which is just on the right from the load, 50 ohm, that's just something what we need to have. That's just a port that I add in the simulation, because here the cool thing about ADS is I'm doing multiple concurrent simulations. So you can see down here, I have an AC simulation, an S parameter simulation, and I'm using harmonic balance. And we can talk about harmonic balance in a second. It's also very cool. But to do S parameter simulations, I need to have ports on what I want to include in that simulation. You can see I have ports on this data, which is my measured data. Well, I also need a port here so I can look at the impedance of my VRM at the output. Right? Okay, so the left on the DC load, these are capacitor. This is just a capacitor. I'm using just a simple RLC model at this point in time. So that's the output capacitor. It is an output capacitor, yeah. Okay. Then I have some just some resistance that I'm adding to simulate the PCB effects, right? Right, just, there's some loss, there's some resistance in the copper, right? Very small, right? You can see it's the micro ohms is what the units are. I think I have it 275 microohms. So it's, and if you would like to simulate the PCB effects, then you change this for S parameter model or something? No, if you really want to simulate the PCB effects, you would import the PCB design into a tool like this. This is PI Pro, and you would extract it, right? So this is basically what I will show you guys I extracted. So this is the Vout node, right? So you can see I'm extracting all these PCB effects from the output inductor, including the output caps. And then also there's a switch node, right? So we talk about the switch node. That's the switch node. This is between the VRM and output inductor. So those are ports that you see there. Oh, and so you create S parameter models for this, and then from this, correct, yeah. And then you include it in the model? In this example, I didn't, but in the next example, we did, which will show. Can we have a look? Can we have a look also on the next example, just very quickly, so everyone see where you included this? Yeah, sure. Yeah. So this is the example where I included the effect, right? Okay. Perfect. Okay, we can go back. Okay. Okay, and you can explain these other parts. Okay. And so then you have your feedback loop, right? So this should make sense to most power supply designers, right? You have a feedback network, which is setting a resistor divider to your air amplifier, which is inside. So all of this is usually inside the VRM, right? Inside the device. Here's our air amplifier, which typically are in most buck regulators today, most suppliers, most like IC designers for like ADI or TI or Renesas, they're going to use a transconductance amplifier. They're cheap, right? And that's what this is basically, that's what this is.
Do we
And
need
then you
to
have
set there something, or?
no, this is one of the blocks, right? So if you pull in the state space average model, you have access to these blocks here. And these are the 4 main blocks you need. You only need 4 blocks, and you build all of this around it. That's it. So you have a buck block, a slope compensator block, you have an amplifier block or an OTA, right? Transconductance amplifier, and then you have a half bridge block, which is well, you need this if you want to do your large signal component. And we'll talk about how this works in a minute.
And what about the R7, C1, C2? So you don't change these. These are on the left from the amplifier.
Oh,
yeah.
These are what's on your schematic. So these are, this is what is on the schematic that is on the board that is connected to this comp pin physically.
Can we see it in the data sheet?
Yes, I think there's a quicker way I can show you. 1 second, I'm trying to think.
Oh, here is something. Here is. No?
There's a quicker way. 1 second. I'm trying to think. The schematic would be here. I want to show you the user guide. Okay, let's go here. And let's go to the user guide. Okay, so there's a schematic in here. Aha, passed it. So, zooming in. 1 second, just being very slow. Okay. So you see this comp pin there, right? So 150 pop, 10K, 10 nano, right? Right. That's 120 puff, 11K, 8 nano. Why are those slightly different? The reason is these are the actual values. There's tolerance in those parts, right? Like, I mean, these are like 10%, 1%, maybe a 20% cap. Depends on what they put on here in the BOM. And so you tune these to match, so you get your response to match from measurement on what's installed. So yes, there is some adjustment you may have to do here to get your overall response, but you could just put in the ideal numbers, right? The nominal, right? So 10K, 10 nano, and then 150 if you wanted to.
Okay.
Go forward from there.
Now let's have a look on the biggest block.
Yeah, so you go from the air amplifier. That's the output of the air amplifier, right? So on the chip, right? If you go to the chip, what we're talking about here, right, is this comp pin right here, right? It's you have access outside the part, but it goes back in like we're showing you in that schematic. And what that is, if we go to a diagram, usually there's a diagram in here, is it goes, I don't think there is one in here. I have a better one I can bring up if not. There we go. Right, so what we're talking about here, let me just comp right here, right? So at the output of the air amplifier right here, right? So this is that pin that we have access to, which we have those components attached to. We go into our slope compensator, right? That's all of this right here, right? That's what this block is, okay? Our slope compensator and then our buck block, right? This is the controller and everything else. So this is everything that I'm encircling here is what we call a small signal model, right, of the Sandler state space average model. This is the large signal component.
Can we have a just quick look also inside of these blocks? I'm just curious.
Sure. Yeah, you can see it's just gonna be a bunch of equations, right? Okay. So it's equations. You have your half bridge inside this small signal model that's creating that half bridge switching effect based on your duty cycle and the output inductor, which is creating that LC filter with your PEN. But you have a bunch of equations that these are all behavior blocks, and these equations are setting the behavior of those blocks. These are standard equations that are in every SPICE power supply book from Steve Sandler. There's another gentleman, I have a bunch of his books, I can't think of his name. He's a French gentleman. He's written tons of great power supply books. But all these equations there's nothing special about these.
But if we would like to just use this model, then we don't really need to like fully go inside of, because you only set these parameters.
You don't have to know anything about those equations. You don't have to understand the math. What you only need to do is give the model the gain parameters that represent the part that you're trying to design.
Then I have a question. If someone would like to simulate this can they download it from somewhere or?
Yeah, so we actually made this workspace available, and I can give it to you in the show notes. This workspace is available if you buy Steve Sandler's book, Power Integrity with ADS. Just gonna grab this one here. So if you buy this book right here, Power Integrity with ADS, this book, Steve on the Picotest website has all these models also available there. This workspace for this example that we're talking about today is also available for download, along with our paper and the slides that we're kind of showing you here.
So you will provide me the link where people can download it and I can place it under the video?
Yep.
Don't forget.
I will. I'm just going to make a note so I don't. Book.
Because this is important. If someone would like to, try to simulate their own model, then it's always good to start with something. And also, I don't think they would be creating these models by themselves.
I'll be honest, it's a little daunting, but I had never made one of these models 2 years ago, and now I would say I'm very good at it, and I understand how to do these measurements very well. But you don't have to be a complete expert, right? It looks scary, right? But so is anything new, right? And I'll be honest, it's not that scary.
I agree.
2 years ago, I didn't know how to do these models at all. And only after a few months, I was able to build my first one and do this. It's not hard. People just have to want to do it. And there's a lot of reasons to do this model. And I'll show you here in a minute why we care.
Okay.
These models over regular spice, right?
So what else we should talk about?
Yeah, so at the output of the buck block, you can see you go to your output inductor, right?
Yeah.
And so you can see there's this duty pin here, right? So this is duty, right? And so the voltage here is going to always be what your duty cycle is. It represents that voltage, right? So whatever your V out over V in is, that's the voltage, right? So if V in is say 5 volts and V out is 1 volt, right? That ratio of 1 over 5 is the voltage you're going to see here. Okay. And so you can see that pin has a name. And so you can see this also has a name right here, right? That is connected. It's like a sheet connector. So what's happening is this duty cycle pin here is connected to this half bridge. That's all this is. This is just a half bridge, right? Just a half bridge. And you can set the parameters of half bridge. In fact, we do. We're feeding it the RDS values, okay? And you can see this half bridge here is again connected. It's a mirror of our small signal model up here, right? And that's what this is, right? It's a mirror of it because this is how we do that large signal component. This is how we get that large signal ripple. Now, the simulation will run without this. If I just deleted this, it'll still run. You're just going to have you're just only going to have the small signal component. But what we're getting by adding this piece and this connection there is we're able to get that large component.
Okay. So what are the other setups? Simulation controllers?
Yeah, so we're using AC, S parameters, and harmonic bound. So AC, right? So we have an AC source right there at the input. And this is how we're plotting our PSR, right? We're doing an AC 1 volt source here. And what you're going to do with an equation is we're going to plot V out over V in using the AC results, right? That's how we plot our gain or PSRR, depending on what we're looking at.
This may be like a not very clever question. Why AC? Why not DC?
Oh, well, remember AC. So when we talk about PSRR is you're using you're sweeping the frequency, right? DC is only one component of frequency, right? You're only looking at one frequency point. Where if we want to plot the PSRR, we want to plot the PSRR
for all the kind of frequencies. So we need to have AC to see response for all the kind of frequencies.
And so you can see here we're going from 50 hertz to 40 megahertz. And then S parameters, again, 50 hertz to 40 megahertz. I think that's where I did the measurements at. And then we have, remember the S parameters are giving us the output impedance. We're also using those. You can also use those to plot your PSRR measured data. You can see I brought one port and I'm plotting it that way. And then you have harmonic balance. So people are like, oh, what's harmonic balance? So you're probably thinking, well, where's the transient? Where's the transient? Where's the time domain simulation? Well, here's the cool thing about ADS. Yes, I can do transient if I wanted to. There's a transient simulator. I can set it up and it'll run. No problem. This model runs just fine with transient. I've done it many times. I, like most people, have gone through the experience where, you know, how you want to run like multiple microseconds of data and you want to have like a lot of fidelity, a lot of time steps. That can take a while. You know, you got to go start the simulation, go get a cup of coffee, and then come back. And maybe it's done. Depends on how big it is, what sort of granular resolution you want in the time points. Have you included the board effect? All of that can take time. Transient is great, but it's also slow. Transient is a pure time domain simulation.
Oh, so it goes through all the frequencies or something?
It goes through every time point. So if I want to do a transient simulation from 0 to 4 microseconds, in this case, with 100 nanosecond steps.
Oh, okay. It takes ages. Okay.
It can, and a lot of times, right, that may not be enough resolution. Maybe you want 10 nanosecond steps, or maybe you want 1 nanosecond steps. 1 nanosecond, right, there are 1,000 nanoseconds in a microsecond. So, oh boy, right, you got to do each one of those. And if you have a multi-phase design, by the way, this state space average model, it works with multi-phase very well. Like I'll show you that really quick. Right here, here's the multi-phase, right? You can see there's 4 phases there, right? It's very easy to run multi-phase with this. And you can see I can plot all the currents per phase. All this is very easy to do. But the reason why I'm talking about harmonic balance versus transient, I still use it, but I love to use harmonic balance. Harmonic balance is not only in ADS. Other tools have it, but I'm an ADS user for a lot of reasons. One of the main is it's the best end-to-end simulator for power integrity. Okay, so what harmonic balance is, it's the native Fourier simulator. And if we talk about here, I'll just bring up a simple example. Very, very, very simple. Okay, why do we use harmonic balance? This is the slide I want. So it's the native Fourier simulator, right? And so the difference between harmonic balance and transient is we are doing all of the analysis in the frequency domain with harmonic balance, and then we do the inverse Fourier transform to get the time domain result, right? And so people are like, well, do you still get the DC point? Yes, you do. It has to calculate that. And then it goes into the frequency domain and does everything at steady state. So it's basically jumping past all those steps in the transient that the transient would do. It's doing all of the simulation in the frequency domain at steady state and doing the inverse Fourier transform, right? So that's what harmonic balance gives you. It's really fast. That's why this model, you see it runs in literally like 3 seconds. This model runs in 3 seconds.
We will see a little bit later.
Yeah, when you're ready, Robert, I'll hit go and we're running. You can see how
we
fast.
explained variables. We didn't talk about.
Oh, variables. Yes.
Yeah.
So just like with a lot of simulators, right, you can have a local variable or a local call for some, component and input, or I like to use variables. This is just a variable. So there's my RI parameter, right? Here you can see it's around 25 milliohms. And you can see that's just going into here, right? FS is my switching frequency. That's a variable down here. You can see it's 500 kilohertz, right? So that's what we use these variables for, right? Just to, if you wanted to have one place to tune a bunch of parameters at a glance, instead of kind of remembering where do I got to go to find that in my simulation.
I understand. Okay, so maybe put it to default because you placed the transient.
Oh, thank you. Yeah, and then the equations this is something you can use. So you can take some, like for example here, I want to take the magnitude of C11, right, which is this guy right here, and I'm using that, and I'm going to call that's my impedance, right? So this is what I call in my data display to plot. I could just plot the magnitude of Z11. I get the same response, but I wanted to give it a bit more of a name that makes sense, right? And so this is an equation that will run in post simulation, and get passed to the data display. So all of these are, right? So you can see doing the measured PSR, right? That's That's 4, that's this one, right? If that makes sense.
Okay, let's simulate it. I'm curious.
Okay, so this is ready to go. Doesn't take much. All we have to do is hit simulate, and it's up. That took 1.69 seconds. Let's look at our data here. So you can move this over. Here we go.
So basically, if you take the physical board and you measure it, you will see this kind of.
Yeah, all this data
signals.
is there for you. I did have to organize it so it looks like this, but yeah, all that data is there. It's there. So you can see let's start from left to right, top to bottom, shall we?
Yeah,
So you can see here's switch voltage, right? We're putting 5 volts in, and you can see we're switching, right? That's about a 500 kilohertz duty cycle right there, right? That makes sense, right? And so 5 volts and off, right? Makes sense so far? The nice thing about harmonic balance is I get all the spectrum content. So this is again why I use ADS. So yes, you can do EMC, you can do radiated emissions with the state space average model. This is what I'm showing you here. And in fact, Heidi Barnes at Keysight, she's the power integrity product owner. She is doing tons of amazing things to enable this more, and people are using this. So you want to do simulation of your board for radiated emissions, you can use this model to do it, and here's the content. It's already there. That's what harmonic balance gives you. So I have the switch current spectrum, so I can see where my energy is. I have the voltage ripple spectrum, so I can see where my energy is. So if you are sensitive to certain things, or maybe you see something from what you built, you can go back and look at your simulation and use this to troubleshoot. Here's the output impedance, right? So this is the output impedance of our VRM, and you can see what I measured, which is the blue line, and my model, which is the red line. They match very well. They correlate very nicely. You can plot your gain of your air amplifier, and then going back down here. Here's our output ripple.
So this is the output from the switching power supply.
Correct. This is the actual ripple. The actual ripple that if somebody were to take a probe and put it right at V out, and you want to see what your voltage ripple looks like and measure the peak-to-peak ripple, that's what this is. And this ripple is a function of that LC network, right? That inductor and the capacitors that make up your PDN, along with the parasitics that are part of your PDN, right? And so that's key.
That's really cool. You can simulate it.
Yep. So this is what you get with this tool, and other tools don't give you this. This is again why I use this tool. And then you have, if I wanted to, I just do an equation, which I have a lot of equations. Most of them are over on this side. And this is all in the workspace, but I can just do an equation and say, tell me the peak, tell me the min, and do the math, and tell me what the ripple is. That's all here, right? I'm just calling a variable based on an equation that I made, right? Again, I'm showing the voltage ripple spectrum. I can show you in different ways in dBm or magnitude. So if you want to do different units. And then here I'm showing you the PSRR, the closed loop PSRR, right? Here's what I measured, and here's what my model looks like, right? So this is for our model, for what we care about for the plant, we only care about the low frequency, right? This range from around 100 hertz or like 1 kilohertz. Now I could easily change this and show you the entire PSRR. That's just a simple parameter change, right? That's easy to do, right? If I were to do something like that, you can see the entire PSRR of your system if you wanted to, okay? So that's easy to do if you want to see how your PDN and PSR are affected. You can even do a cascaded VRM, right? So if you have a buck to an LDO or a buck to a buck, and you want to do that in ADS and look at your total system PSR, I've done that many times. That's easy to do here, and you can see, okay, if I make this bomb change, does it really help me or hurt me? And you can show it in the model. Here you can see based on that load, right? Remember, it's we have about a 1 volt output, and you can see that here, right? So
yeah, I can see it. Yeah, right? I noticed that.
Yep. And you can see, right, it's hovering right around 10 amps. Exactly, it's 9.9. I'm using an equation that tells me the mean of this waveform. And you can see it's 9.9, and that makes sense, right? We have a 0.1 ohm resistor hanging on the output, 1 volt. Okay, that makes sense.
Cool. Cool to do. So cool.
Yeah, and so here's your inductor current spectrum, right? So if you wanted to see what that spectrum looks like, again, you can see I'm clipping there. That's easy to adjust. I just changed these units. I just scaled this so it looks okay for people to read it. Again, I'm showing this in magnitude and then dBm here. And then we talked about the Bode, right? People want to see the Bode plot. Well, we already have that with impedance. Now I can still do a Bode plot with ADS. That's easy to do, very easy. But I already have off impedance and on impedance, so I just do an extracted loop gain. Remember what we
Okay,
said a second ago?
so the last one, blue and red, that's not like measured and simulated, but it's
No,
on off.
no. Remember loop gain, right, is off over on minus one, right? Let's go back to the schematic, right? Z11 is on,
Mm-hmm.
right? I have an off in here. Where did I put my off? 1 second. My off is somewhere in here. I'm calling this one. Yeah, so Z22 is off, right? So I'm using the measured data. I could have made another block for this and just attached it there, but I'm just using the measured data for off. So Z22 is off,
Mm-hmm.
and Z11 is on, right? So we know from control theory and loop, what a loop gain is, right? Off over on minus one is our loop gain, right? And so all we're doing is we're plotting the dB of t, right? So there's our extracted loop gain, right? And you can plot the phase of it, which is what I'm doing here on the blue line. And so, hey, look, there's your Bode plot, right? It's right there if you really want it. But I look at impedance for stability. Impedance tells me a lot, and I can tell you what you see in impedance using NISM, you will get correlation every time with a Bode plot. But the caveat is a Bode plot is only looking at the control loop. It's not including the PDN. So why would I only want to look at one part of my system? I use impedance because I can look at the entire system, right? And that's more powerful. So and then again, just to reemphasize, what do you do when you have a PMIC and you don't have access to the control loop? How do you do a Bode plot? You can't. So Steve's talked about this a lot, right? I mean, there's some interesting stuff out there, and I love NISM. It's easy to use and it's free. It runs in ADS. It runs on every VNA for free. So Picotest made it free. But yeah, so this is it. This is the entire model. So the next
So now
step.
I have a question. So did you compare this with the real system?
Yeah, that's next step. Let's do that. Let's do that. So I have it ready to go, right? You ready for that? Okay, so here's our ripple. Okay.
It's not exactly the same.
No, what is that right there? Okay, so we have this looks good, but then what the heck is that? Nobody wants this additional like resonance in your ripple. This doesn't look right. That's not correct. And if you look right, okay, so there's 3 microseconds, there's 4 microseconds. You can see from here to here, that's about a 1 microsecond period. So it's like a 1 megahertz additional oscillation. Why is this not in our model? Huh.
Because we are not simulating real PCB.
Ah, yes, right. This is again, why would you not want to include the PCB? What does the PCB give you? It gives you a lot. So let's do that, right? So what I did, let me move this here, right? So what I did is we showed this, right? So we extracted the switch node, okay? And we extracted the V out node, right? So this makes sense, right? With all the caps, right? And everything, okay? And we brought that into our model, right? So there's the output node. And if I push into here, right, you can see all of my caps are on there, right? This is a touchstone model.
So this is
right?
the PCB itself, yeah?
This is the V out node of the PCB, yeah.
And these others are components, the
These
capacitors.
are all the caps that are installed on that V out, right? So one model. I have a cap that's hanging at each respective port that was extracted, right? Remember, there's inductance between that cap and the connection. There's inductance in that path from where that cap connects to when it actually connects to the PDN. There's inductance there. How do you model that? And that inductance matters. This is where everything matters. Remember, this is an 18 amp supply. What do you do if it's 100 amp or 1,000 or 500 or 2,000? And so this is where the PCB effects have to be included in your PCB.
So that's why the PCB model has so many outputs, because that kind of corresponds the position of specific capacitor.
Exactly. Yeah, exactly. So if I highlight this here for you, right? So I want to do V out, V out, V out, V out. So if I highlight, right, there are 1, 2, 3, 4, 5, 6 times 2, 12 output caps. You can see it right there, right? 12 output caps. And you see all those ports, right? Right? Some of them aren't installed on the physical artwork, right? And you can see when you look at this, right, not all those caps are installed, right? So if you look here, there are 2 that aren't installed right there. So, okay, that means I made a note. You see, not installed on EVM, not installed. Those aren't installed. I just disabled them, right? They're not included in the artwork. Same with this one. I made a note. That one's not installed, right? So that was actually where we made our measurement, if you recall, right? C23. So I've built a real model, very close to real, right? And attached it to my simulation here, right? That's all I changed. I injected the V out node. Now I can add the switch node. In fact, I did do that in another part of the workspace. And you can see that effect also. But it wasn't important for this demo here.
Okay. So I'm curious. Now, what happened?
You want to simulate?
Yeah.
Is that what you want? Let's do it. Let's simulate. All right, it's very quick. And I included the PCB effects. Wow, 4 seconds and it's done. Hey, do you remember that you just saw? There it is. So all I did was add in the PCB effects. Wait a minute. Look at that. The exact same issue that we saw in measurement just by including the PCB effects. Look, our impedance is even a little different, right? So this is why this is really, really important, right? This is really, really important.
I would like to highlight, sorry for interrupting, but I really would like to say now, like, how important these PCB effects are for the circuits. And you can see it's just copper and capacitors, and they make difference.
Makes a huge difference, right? Because there's inductance and everything. I'll put it this way, right? If you're not including PCB effects in your power supply or power integrity simulation, your answer is always wrong. It's already wrong. Will never be right. And that's why we did this paper, right? This is why it's hard today to be an engineer, right? There's a lot you have to do, but here we're showing you it's not that hard, right? It's not that scary. It's not hard to build this model. It's not hard to extract this artwork and do this.
And this is only 10 amps. Imagine what will happen if it's 100 amps.
Yeah, you have that. That's, and you know, from an EMC perspective, you can actually see it here, right, in the spectrum. You can see this additional energy here. That's because of this additional periodic ripple that's in your in their output response that you don't necessarily want. No power electronics guy wants this.
So did you fix this?
Yeah, well, the question is, how do you fix it first, right? How do you fix it? So for me, I go back to my bread and butter. And this is, I can't emphasize this enough, impedance. Remember what I said a second ago? If you remember one thing, noise follows impedance always, right? So remember, V equals IR. R is, if we change that R to a Z and we've made it into the complex term of impedance, right? Real and imaginary. Now we have the impedance. Oh, hey, wait a minute. We have the output impedance right here of our PDN with our V out. And so you can see by adding in those board effects, here's my VRM. This is the control loop of my VRM. This is output inductance of the VRM's control loop. And, oh, I can see this is a volt cap here. And I go up and I see, oh, what's that? Wait a minute. Right there at 1 megahertz. Didn't we say this is like a 1 megahertz period? Look at that, right? Right around 2 microseconds to just after this is about 1 microsecond, right? So it's 1 megahertz period. What do you know? This looks like the smoking gun, right? There's a resonance right there at 1 megahertz. That's it, right? Well, how do I figure out what that is? Well, what I'm not showing you is the off measurement. And if we go back and look at the off measurement, you would see that this is part of that passive part of the PDN. This is not part of the VRM.
Okay, I would like to clarify. So off measurement, it means when power supply is off, and you do, yeah.
Exactly, right? And so I think I have a great slide. Let me see if I have it in the slides. I think I have it in here. I show you the on and off. I'm trying to remember if I put it in there or not. I think I did. I can't remember if I did or didn't. But if not, I do it all the time, right? So it'd look like something like this, right? This is just the cap, right? It's just passive. The passive nature. You know, I don't have that in here, but it's easy for me to show, and I can show you that later, Robert, if you want to see it.
So basically, the influence from the loop and power supply would be gone. It would just go down, 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 and you would only see the influence of the capacitors on the board.
Correct, right? And so the way I would show that is right here, just like this. So I'm going to just do, I think it was D22, right? So Z22, let's do the magnitude real quick. I'm going to make this like a little pop. Let's make it green. I'm going to make it pop so you can see it. And there you go. Right. So there's off.
This was really quick.
And so you can see right there in the off measurement, right? You see there's a clue already. I have a little bit of a 1 megahertz dip there, right? The clue was already there for me, right? So why don't I see that in my simulated measurement? The answer is because in this simulated measurement, remember, I'm not using the board effects, right? So I don't have an inductance. And what I measured, I actually measured a different board when I made this measurement. So they're the same, but it didn't have that cap. That's what I'm gonna show you installed, so a slightly different configuration. So when I found this later, I made a very good example. But you can see right there, there's that little blip that I was just pointing at, right? That's part of our problem. So let's go and figure out, well, how do we figure this out? Well, we showed that there's a 1 megahertz dip there in our impedance, and that's probably a correlating factor. What I did to make this very easy is let's look at our V out node, right? So we have 12 output caps, right? And I have a better picture that makes it easier to look at. And if you look at these 12 output caps, you have a bunch of 330s, right? There are 8 of them, right? Not all of them are installed, but you have 8 of them, okay? And then you have two 22 mics and then 2.1s, right? Of these 330 microfarads, well, if you guys understand the impedance of a bulk cap, like
it would
a 330,
be lower, somewhere lower.
Yeah, it's gonna be a much lower impedance, like down here, right, in this region, okay? And if you look at those 0.1 microfarads, right, 100 nanos, if you want to use that unit, these are gonna be up here, right? This is much higher in frequency, right?
When you say up, it means same graph, but the dip would be.
Yeah, they're going to resonate higher in frequency. So if you look at where the 330 microfarads are going to affect our impedance in this region.
Can you show with cursor how the graph would look?
Oh yeah, well, these are tantalum, so they're going to have a flatter response because they have ESR, and then the inductance of the package is going to kick in and go up like the 0.1s are going to be somewhere like this, and then resonate, and then go up like that. But we do have 222 microfarads. Well, that's interesting. And the asterisk there means only one of them's installed. In fact, you can see this board I modified, but on the one that I have, and this is the way TI was shipping it, okay, only one of these 22 mics was installed, right? Remember I showed you my measurement point? Yes. It was C23. C23 wasn't installed. Well, C24 is installed. Okay, well, process of elimination, right? You can see here, okay, if we plot just from Murata, right, a 22 mic, the same cap, you can see, oh my goodness, it's resonating right around 1 megahertz. I think we found our smoking gun. What do you think, Robert? So this is how easy it is to do an ADS, right? All I did, right, let me go back to this, okay? All I did was I went into this model, and it was C24, right? I'm just going to disable it. This is the same as desoldering it from the physical PCB. It's the same as clicking it off. It's gone. It's removed. All right. Now let's resimulate. Okay. Remember what we saw here? Let's go back here. There's your response. Boom. Just like that. It's gone. Removed one cap. The response is gone. So, and you can even see it, right? Let's go look at our impedance. Hey, look at that. Do you remember that big dip there that we had at 1 megahertz? It's gone. So we just showed you how to figure out that impedance, the board effects, right? Understanding the passive nature of your PDN, what it does to your power supply, is important from a power integrity perspective. So why would you include it? And how easy it is to troubleshoot and fix it, right? And if you want to go a step further and see how good you can get it, this is how good you can get it.
So this is after you remove the capacitor from the board. One is measured, one is simulated.
Yep, that's the same waveform I just showed you down there. I've just stretched it out and scaled it. So this is measured using a text scope. So Steve made the measurement. That's the yellow one. And this is that simulated waveform you just saw. And you can see the scales are verbatim lined up, right? They're 100% identical. 1 volt, 1.008 is up here, 1.006. All the axes are 100%, 4 to 4, 3 to 3, 2 to 2, 1-to-1. So you can even see that the ripple matches verbatim. Now, again, that goes back to I had the gain value set correctly because we made the measurement-based model. You did not have to do that if you're not doing this. I wanted to do this to show people that you can get this, right? And so this is how you would do a correlation. And you can see the ringing in our waveform is lining up with what was measured. I mean, look how cool that is. So this is what you get. So you're wondering, oh, how accurate is it? I don't think you can get much better than that, right? I mean, that's the real thing. That's it. So yeah, pretty cool, huh?
Two things which are really cool. First, you can simulate it and get the results, the real results. That's like super cool.
Seconds.
And the second, in seconds, yeah, even faster than you would measure it.
Yeah, Steve and Heidi like to say it's blazingly fast, and they're right. It's really fast.
And
cool.
Second amazing thing is how one unfitted capacitor will influence your power supply output. How is this possible? Like, you know,
the placement matters because the placement is adding inductance, which is affecting the PDN here. And this is the cool thing about tools today. You can use tools to figure out, is this a problem, right? Because in the real world, you need to be able to model the real world today to be agile and to get the right answer. And this is why, again, I use this tool to do that. When you want to ship something and you have a problem, whether it's EMC or Ripple or whatever, how do you troubleshoot it? Well, I just showed you how, really practically.
So Ben, what do you actually do?
Me?
Yeah.
Oh, so I work for a big, large aerospace defense contractor. I design and develop and integrate advanced ASICs, as well as I have my own consulting business where I specialize in signal integrity, power integrity, EMC modeling. That's what I do. So I live in this stuff. I love this stuff. I have fun teaching and helping others learn this, and I love doing this and solving hard problems. Yeah.
And you know, you will be on DesignCon. So if
will,
someone would like to meet you, then DesignCon.
Come say hi. Yeah, reach out to me on LinkedIn, say hi. Ben, I saw your video or whatever, and yeah, I'll connect with you. My company, my consulting business is Signal Edge Solutions. You can just email me. I'll have Robert put in the show notes. You can go to my website. This paper is on my website, so you can just download it. It's free. You don't have to do anything. It's just on the publications page. But yeah, I'll be at DesignCon. Steve and Heidi and I are doing a few things together this year. We're having a lot of fun.
Can we open website? I'm just, you know.
Yeah, you want to show the DesignCon website?
Yeah. Because I would like to show also Steve, because you know, maybe people would like to meet there also. Steve and Heidi.
Yeah, they're awesome. If you haven't met Steve or Heidi, you really got to meet them. They're so fun to work with. I'm grateful every day that I get to work with them, and yeah, and learn, and we get to learn from each other. But yeah, we have a lot of fun. So yeah, this is
which one is yours?
So I am doing a few things with Steve and Heidi. So the thing that people are probably most interested in is our paper, which let me find
maybe
it.
search for speaker.
I'm going to do by track 10.
Okay.
So that's easier. Right here. So we're doing a panel.
2000 amp.
Yeah, so this is the paper I did with Steve.
That's why you simulated. Okay.
Yeah, so this matters, right? So this is the paper I did with Steve, Heidi Barnes, Uni from Monolithic Power Systems, so MPS, and Aiden Ezra from Broadcom. So we had a lot of fun. It's not easy to design for 2000 amps, but guess what? That's where ASICs are going and where they are today. How do you design? How do you model? How do you simulate? How do you measure? What are the challenges? And so we talk about all that stuff. So it'll be a lot of fun. And then we're doing a panel, right? A panel, Steve, Heidi, myself, and some others. Steve, Heidi, and I are also doing a chip head about calibration, advanced calibration for PDN measurements and impedance using the 2-port probe. There's some cool challenges we're going to talk about there. And then I have a tutorial I'm doing with some other colleagues, and then I have another chiplet I'm doing with one of my mentees, Will McCaffrey. Yeah.
Okay. So
a lot of fun stuff.
Thank you so much, Ben. I had no idea how to simulate power supplies. Now, at least I'm not going to say I know how to do it, But at least I have idea how this can be done, and
Yeah,
and it was very interesting because I always thought simulating power supply is based on the chips, but no, you don't have to simulate based on specific chip. You can
yeah.
just know behavior
Exactly.
of power supply. You
Yeah,
know how power supply works, and
yeah,
you just feed it with the parameters of your specific
exactly.
setup, and then you
Yeah.
can do the simulation and get really accurate results. This was like, wow,
Isn't that
cool.
cool? I mean, and you don't have to be an expert in these things to do it. I mean, there's
You
plenty
need to
of
be
content out
expert.
there. The papers are out there. You have Steve's book. I mean, there's lots
you,
of resources.
you need to at least understand all these measurements and all the parameters what you explain. I had no idea what kind of parameters you were talking about, but I'm pretty sure everyone who is working in power supplies, they know exactly what you meant. And also, if they don't know, they can always search on internet and find out.
Yeah, there's tons of content. TI has content. ADI, oh, they all have stuff out there. Tons of stuff. And if not, there's great books by Basso, Chris Basso. That's what I was trying to think of earlier. He's an engineer. He's been around for a long time. Worked on Semi. I forget where he is now, but he's got lots of great books on power supply design. There's tons of individuals out there like that.
Mm. Okay, thank you so much, Ben, for helping me with this video.
Yeah, thanks for having me, Robert. It was a pleasure.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.